Hi, I'm Mike Hobbins. So the charge from Indices for my talk was a lot, basically to discuss the implications of climate change on one half of the drought imbalance, that of its demand side. In putting this talk together, my struggle has been to paint a coherent picture without clouding the message with detail or making an over-expansive attempt to cover everything. What I hope to show is that the demand side of drought is pretty poorly characterized, at least with respect to long-term trends and projections, mainly due to process misunderstanding and misrepresentation. I'll try to issue some warnings and point to some missing pieces. Hopefully this will provide some context for when we meet in person. First off, what do we mean by drought's demand side? Well, if we define drought as an impactful imbalance between the supply of moisture to the surface and the demand for the return of moisture from the surface, then it's easy to see the supply side as precipitation. What's not so clear is the demand side, the return flux. The actual return flux to the atmosphere is ET, which is a function of moisture availability at the surface and the demand for that moisture in the atmosphere, or the evaporative demand. Now, this evaporative demand is a physical function of radiation to and at the surface, that is, sunshine and air temperature, and the ability of the overpassing air to absorb the evaporated moisture and to transport it away, that is, humidity and wind speed. What evaporative demand should not be is just a function of temperature, or of temperature and radiation alone. This will become important later on. Now, we're probably familiar with a variety of drought indices that examine drought as a function of some of these fluxes and states, and here I've listed a few of them. For better treatment of the variety of drought indices and their uses, please see the handbook shown at top right. So this talk will mainly treat ET and evaporative demand, and to some degree soil moisture. How do ET, evaporative demand, and soil moisture relate under drought? Well, hopefully this graphic shows us as we progress through drought from left to right. Here we see their relations as that drought develops. Evapotranspiration may increase because it's warmer or sunnier, and evaporative demand will also increase in response to those same drivers. But eventually evapotranspiration will crash as moisture becomes no longer available, but evaporative demand, due to feedbacks from the drying land surface, that complementary relationship, due to those feedbacks, evaporative demand increases. This makes it a really robust metric of drought and led to the development of EDI, the Evaporative Demand Drought Index. And here we see that complementarity between actual ET in the dark blue and evaporative demand in the purple, exhibited in long terms of observations of evaporative demand from evaporation pans and actual ET from water balances across CONUS. This was the first confirmation of the complementarity as an observable fact, in this case across CONUS. And we do also see the complementary relationship in climate scale projections from coupled Earth system models. Here on the left, for the northern Great Plains, we see evaporative demand increasing between the two periods, primarily in response to rising temperature. The cloud of blue dots moves leftward to create the red cloud, indicating that while soil moisture declines, actual ET remains about the same. This may be an aridification signal in the face of increasing precip. A similar, though more muted signal appears in the Four Corners region on the right-hand side. The point here is that the best current models can capture this complementary relationship. So what then explains the evaporation paradox? In this context, that would be when evaporative demand is observed to be declining despite increasing warming. Well, we looked at this in Australia at a bunch of pans from this period, 1975 to 2004, and we saw a mix of increasing and decreasing pan evaporation shown here on the very left-hand side of the graphic, where the mean trend is negative 2 millimeters per year. And that's a function of the addition of an advective trend of negative 2.6 millimeters per year, that's that center bottom graphic, and a radiative trend of plus 0.6 millimeters per year. The advective trend then actually can be further decomposed into its components of that which derives from vapor pressure deficit and that which derives from wind speed. And we can track those forcings on evaporative demand, and we see that there's really no effect of a VPD trend. But there's a huge effect of a wind speed trend, negative 2.7 millimeters per year. So if you add up the radiative and the wind speed trends, they add up to the overall evaporative demand trend. Point here being that it is wind speed that is driving the trends in evaporative demand, the declining trends in evaporative demand. And the evaporation paradox is no more than the fact that evaporative demand is driven by a bunch of different drivers: temperature, humidity, wind speed, or radiation, not just temperature. So much for trends in observed evaporative demand. Here, we see a variety of trends in evaporative demand as estimated by 5 different reanalyses, but all using the Penrose-Monteith reference ET equation. This is a gold standard for estimating evaporative demand, if you will. Presumably, these differences are a function of the different drivers of each of the reanalyses and their assimilation of observations. But note, if you were a water manager planning infrastructure developments in the upper Colorado, where different reanalyses show different trend directions and magnitudes, you would definitely want to know which of these to use. And here we show the same analysis, but now presented in units of standard deviation. This shows us how far outside the range of variability the changes over the period are. You see that over much of CONUS, the trend signal is emerging from a 40-year range of variability. And here we see yet another process understanding advance, where Milley and Dunn, in an upper Colorado River Basin-wide study of declining stream flow, they looked at an elevation-dependent albedo in a fairly sophisticated hydrology model with a radiation-based evaporative demand, and they captured some large-scale processes that had before not been captured: the reduction in albedo due to snow cover loss and the increase in actual ET from that increasingly bare ground. And they showed a stream flow loss of 9.3% per degree of warming. If you're one of the 40 million people who rely on the Colorado River for your water, that's scary. And here we see trends in satellite-derived ET. Sure, there are some assumptions, of course, converting remotely sensed data to ET, but what we're showing here is there are significant increases in ET over land, and they're caused by increases in transpiration and evaporation from interception, partially counteracted by decreases in evaporation from bare soil. These contrasting trends are primarily driven by increases in vegetation and leaf area index, and dominated by greening. The overall increase in transpiration is about twice the decrease in bare soil ET. But the significant point here is that these opposing trends are not simulated by most CMIP-5 models. And this highlights the importance of realistically representing vegetation changes in Earth system models for predicting future changes in the energy and water cycle. And as if to show the danger of relying on reanalyses for your actual ET and the model assumptions therein, here's a study of 11 global ET datasets, where 5 models showed negative trends, 6 models showed positive trends, but the overall average was a decline in actual ET. So models really are important. The models and the assumptions really are important. So the selection of an ET dataset should consider its spatio-temporal uncertainty before it's used in any water balance study, aiming to infer hydrologic change. And now I've thrown this graphic in here just to show that there are significant vegetation and greening differences that are regional across the globe. On the top you can see some greening regions, on the bottom you can see some browning regions, I guess. So much for our moves towards increasing our process understanding. Let's briefly touch on a more insidious threat to understanding the implication of climate change on the demand side of drought, that of poor process representation. Finally, I come to look at drought projections using some of these ideas we've talked about in the past. So here, we've looked at 3 different parameterizations of evaporative demand. From the left, we're looking at purely physically based, the best one. In the middle is the worst one, the temperature-based, Hargreaves-Samani, for example. And on the right-hand side, it's a radiation-based, it's halfway between good and bad, let's say. And they're both driven by 2 different Earth system models, as you can see, each row. So they are very different. These are projected trend changes in evaporative demand relative to this 1976 to 2005 period. They're very different depending on what parameterization is used and what driving model is used. And they are very different in terms of what they show for drought risk in the future. Each of these panels shows drought risk evolving from 1950 upwards to 2100 for each of those parameterizations of evaporative demand and the Earth system models. And as you can see, if you relied on a temperature-based evaporative demand, we would be drying up and blowing away by the year 2100. These are very important distinctions. So just to sum up very briefly, I just try to point out that these trends analyses in the demand side of drought suffer from both poor understanding of dynamics and then a poor representation of dynamics. Also note that we really need a physically based evaporative demand to improve trends analysis of drought's demand side. You cannot use a temperature-based evaporative demand. Adding those remaining drivers really affects predictions, but we don't know yet if those remaining drivers are predictable at climate scales. For example, one of the most important drivers is wind speed. In general, evaporative demand trends are clearer than evapotranspiration trends, but in both cases, models matter. It's really important which models you use. There are a few other comments here that maybe we can talk about when we get together in person.